In mathematics, the orthogonal group in dimension n, denoted O, is the group of distance-preserving transformations of a Euclidean space of dimension n that preserve a fixed point, where the group operation is given by composing transformations. Equivalently, it is the group of n times n orthogonal matrices, where the group operation is given by matrix multiplication. And an orthogonal matrix is a real matrix whose inverse equals its transpose. The determinant of an orthogonal matrix being either 1 or -1, an important subgroup of O is the special orthogonal group, denoted SO, of the orthogonal matrices of determinant 1. This group is also called the rotation group, because, in dimensions 2 and 3, its elements are the usual rotations around a point or a line. In low dimension, these groups have been widely studied. See SO, SO and SO. The term orthogonal group may also refer to a generalization of the above case. The group of invertible linear operators that preserve a non-degenerate symmetric bilinear form or quadratic form on a vector space over a field. In particular, when the bilinear form is the scalar product on the vector space Fn of dimension n over a field F, with quadratic form the sum of squares, then the corresponding orthogonal group, denoted O, is the set of n times n orthogonal matrices with entries from F, with the group operation of matrix multiplication. This is a subgroup of the general linear group GL given by where quart is the transpose of Q and I is the identity matrix. This article mainly discusses the orthogonal groups of quadratic forms that may be expressed over some bases as the dot product over the rails. They are the positive definite quadratic forms. Over the rails, for any non-degenerate quadratic form, there is a basis on which the matrix of the form is a diagonal matrix such that the diagonal entries are either 1 or -1. Thus the orthogonal group depends only on the numbers of 1 and of -1, and is denoted O, where P is the number of ones and Q the number of negative ones. For details, see indefinite orthogonal group. The derived subgroup omega of O is an often studied object because, when F is a finite field, omega is often a central extension of a finite simple group. Both O and SO are algebraic groups, because the condition that a matrix be orthogonal, i.e., have its own transpose as inverse, can be expressed as a set of polynomial equations in the entries of the matrix. The Cartan-Giudone theorem describes the structure of the orthogonal group for a non-singular form. Name: the determinant of any orthogonal matrix is either 1 or -1. The orthogonal n by n matrices with determinant 1 form a normal subgroup of O known as the special orthogonal group SO, consisting of all proper rotations. Is the kernel of the Dixon invariant, discussed below. By analogy with GLSL, the orthogonal group is sometimes called the general orthogonal group and denoted GO, though this term is also sometimes used for indefinite orthogonal groups. So, the term rotation group can be used to describe either the special or general orthogonal group. In even and odd dimension, the structure of the orthogonal group differs in certain respects between even and odd dimensions. For example, over ordered fields the -I element is orientation preserving in even dimensions, but orientation reversing in odd dimensions. When this distinction is to be emphasized, the groups may be denoted O and O, reserving n for the dimension of the space. The letters P or R are also used, indicating the rank of the corresponding Lie algebra. In odd dimension the corresponding Lie algebra is, while in even dimension the Lie algebra is. Difference between O and SO in even dimensions. In 2 dimensions, O is the group of all rotations about the origin and all reflections along the line through the origin. SO is the group of all rotations about the origin. These groups are closely related. SO is a subgroup of O, since any 2 reflections gives a rotation. More generally, in any number of dimensions an even number of reflections gives a rotation, and a rotation followed by reflection, or vice versa, produces a reflection. Therefore, the rotations define a subgroup of O, but the reflections do not define a subgroup. A reflection through the origin may be generated as a combination of one reflection along each of the axes. The reflection through the origin is not a reflection in the usual sense in even dimensions, but rather a rotation. In 2 dimensions it is the only non-trivial rotation that when applied twice gives the identity. It is its own inverse in any number of dimensions. In 4D it is isoclinic, and if that classification were generalized it would be isoclinic in every even number of dimensions. Over the real number field. Over the field R of real numbers. The orthogonal group O and the special orthogonal group SO are often simply denoted by O and SO if no confusion is possible. They form real compact Lie groups of dimension n. 2. O has 2 connected components, with SO being the identity component, i.e., the connected component containing the identity matrix. Geometric interpretation. The real orthogonal and real special orthogonal groups have the following geometric interpretations. O is a subgroup of the Euclidean group P, the group of isometries of Rn. It contains those that leave the origin fixed. O equals EGL. It is the symmetry group of the sphere or sphere and all objects with spherical symmetry, if the origin is chosen at the center. So is a subgroup of E+, which consists of direct isometries, i.e., isometries preserving orientation. It contains those that leave the origin fixed. So equals E+, GL equals EGL+. It is the rotation group of the sphere and all objects with spherical symmetry, if the origin is chosen at the center. Plus or minus I is a normal subgroup and even a characteristic subgroup of O, and, if n is even, also of SO. If n is odd, O is the internal direct product of SO and plus or minus I. For every positive integer k, the cyclic group Ck of k-fold rotations is a normal subgroup of O and SO. Relative to suitable orthogonal bases, the isometries are of the form, where the matrices R1, Rk are 2 by 2 rotation matrices in orthogonal planes of rotation. As a special case, known as Euler's rotation theorem, any element of SO is rotation about a uniquely defined axis. The orthogonal group is generated by reflections, as in a Coxeter group, and elements have length at most n. A longest element is reflection through the origin, though SO are other maximal combinations of rotations. The symmetry group of a circle is O. The orientation-preserving subgroup SO is isomorphic to the circle group, also known as U. This isomorphism sends the complex number exp equals cos phi plus isim phi of absolute value 1 to the special orthogonal matrix, the group SO. Understood as the set of rotations a three-dimensional space, is of major importance in the sciences and engineering, and there are numerous charts on SO. Maximal Taurian WEYL groups. A maximal torus T for SO of rank n is given by the block diagonal matrices where the Rj are 2 by 2 rotation matrices. The image T times 1 of the same torus under the block diagonal inclusion is a maximal torus for SO. The WEYL group of SO is the semi-direct product of a normal elementary abelian 2 subgroup and a symmetric group, where the non-trivial element of each plus or minus 1 factor of plus or minus 1 n acts on the corresponding circle factor of T times 1 by inversion, and the symmetric group Sn acts on both plus or minus 1 n and T times 1 by permuting factors. The elements of the WEYL group are represented by matrices in O times plus or minus 1. The Sn factor is represented by block permutation matrices with 2 by 2 blocks, and a final one on the diagonal. The plus or minus 1 n component is represented by block diagonal matrices with 2 by 2 blocks, either with the last component plus or minus 1 chosen to make the determinant 1. The WEYL group of SO is the subgroup of that of SO, where Hn-1 less than plus or minus 1 n is the kernel of the product homomorphism plus or minus 1 n plus or minus 1 given by, that is Hn-1 less than plus or minus 1 n is the subgroup with an even number of minus signs. The WEYL group of SO is represented in SO by the preimages under the standard injection SO of the representatives for the WEYL group of SO. Those matrices with an odd number of blocks have no remaining final -1 coordinate to make their determinants positive, and hence cannot be represented in SO. Low-dimensional topology. The low-dimensional orthogonal groups are familiar spaces. O equals S0, a two-point discrete space. SO equals 1. SO is S1. SO is RP3. SO is doubly covered by SO times SO equals S3 times S3. Homotopy groups. In terms of algebraic topology, for n greater than 2 the fundamental group of SO is cyclic of order 2, and the spin group spin is its universal cover. For n equals 2 the fundamental group is infinite cyclic in the universal cover corresponds to the real line is the unique connected twofold cover. Generally, the homotopy groups πk of the real orthogonal group are related to homotopy groups of spheres, and thus are in general hard to compute. However, one can compute the homotopy groups of the stable orthogonal group, defined as the direct limit of the sequence of inclusions. Since the inclusions are all closed, hence cofibrations, this can also be interpreted as a union. On the other hand, Sn is a homogeneous space for O, and one has the following fiber bundle, which can be understood as the orthogonal group O acts transitively on the unit sphere Sn, and the stabilizer of the point is the orthogonal group of the perpendicular complement, which is an orthogonal group one dimension lower. Thus the natural inclusion OO is connected, so the homotopy groups stabilize, and πk equals πk for n greater than k plus 1. Thus the homotopy groups of the stable space equal the lower homotopy groups of the unstable spaces. From Bott periodicity we obtain omega 800, therefore the homotopy groups of O are 8-fold periodic, meaning πk plus 8 equals πk, and one needs only to list the lower 8 homotopy groups. Relation to co-theory. Via the clutching construction, homotopy groups of the stable space O are identified with stable vector bundles on spheres, with a dimension shift of 1. πk equals πk plus 1. Setting co equals bo times z equals omega minus 1 O times z, one obtains computation and interpretation of homotopy groups. Low-dimensional groups. The first few homotopy groups can be calculated by using the concrete descriptions of low-dimensional groups. Pi0 equals pi0 equals z2, from orientation preserving, reversing and hence stably. Pi1 equals pi1 equals z2, which is spin comes from SO equals rp3 equals s3. Pi2 equals pi2 equals 0, which surjects onto pi2. This latter thus vanishes. Lie groups. From general facts about Lie groups, pi2 always vanishes, and pi3 is free. Vector bundles. From the vector bundle point of view, pi0 is vector bundles over S0, which is 2 points. Thus over each point, the bundle is trivial, and the non-triviality of the bundle is the difference between the dimensions of the vector spaces over the 2 points, so pi0 equals z is dimension. Loop spaces. Using concrete descriptions of the loop spaces in Bott periodicity, one can interpret higher homotopy of O as lower homotopy of simple-to-analyze spaces. Using pi0, O and O, you have two components, co equals bo times z and ksp equals bsp times z have countably many components, and the rest are connected. Interpretation of homotopy groups in a nutshell. Pi0 equals z is about dimension. Pi1 equals z2 is about orientation. Pi2 equals z2 is about spin. Pi4 equals Z is about topological quantum field theory. Let R be any of the four division algebras R, C, H, O, and let LR be the tautological line bundle over the projective line P1, and LR, its class in K-theory. Noting that Rp1 equals S1, Cp1 equals S2, Hp1 equals S4, Op1 equals S8, these yield vector bundles over the corresponding spheres, and Pi1 is generated by LR. Pi2 is generated by LC. Pi4 is generated by LH. Pi8 is generated by Lo. From the point of view of symplectic geometry, Pi0, Pi8 equals Z can be interpreted as the Maslov index. Thinking of it as the fundamental group Pi1 of the stable Lagrangian Grassmannian as U, O omega 7, so Pi1 equals Pi1 plus 7, over the complex number field. Over the field C of complex numbers, O and So are complex Lie groups of dimension n, 2 over C. O has two connected components, and So is the connected component containing the identity matrix. For n2 these groups are non-compact. Just as in the real case So is not simply connected. For n greater than 2 the fundamental group of So is cyclic of order 2 whereas the fundamental group of So is infinite cyclic. Over finite fields. Orthogonal groups can also be defined over finite fields Fq, where Q is a power of a prime P. Over finite fields of characteristic not equal to 2, orthogonal groups come in two types in even dimension, O plus and O minus, and one type in odd dimension. O. If V is the vector space on which the orthogonal group G acts, it can be written as a direct orthogonal sum as follows, where Lie are hyperbolic lines and W contains no singular vectors. If W is the zero subspace, then G is of plus type. If W is one-dimensional then G has odd dimension. If W has dimension 2, G is of minus type. In the special case where n equals 1, O is a dihedral group of order 2. We have the following formulas for the order of O, when the characteristic is not 2. If -1 is a square in Fq, if -1 is a non-square in Fq, the Dixon invariant. For orthogonal groups, the Dixon invariant is a homomorphism from the orthogonal group to the quotient group Z, 2Z, taking the value 0 in case the element is the product of an even number of reflections, and the value of 1 otherwise. Algebraically, the Dixon invariant can be defined as D equals rank modulo 2, where I is the identity. Over fields that are not of characteristic 2 it is equivalent to the determinant. The determinant is -1 to the power of the Dixon invariant. Over fields of characteristic 2, the determinant is always 1, so the Dixon invariant gives more information than the determinant. The special orthogonal group is the kernel of the Dixon invariant and usually has index 2 in O. When the characteristic of F is not 2, the Dixon invariant is 0 whenever the determinant is 1. Thus when the characteristic is not 2, So is commonly defined to be the elements of O with determinant 1. Each element in O has determinant plus or minus 1. Thus in characteristic 2, the determinant is always 1. The Dixon invariant can also be defined for Clifford groups and pin groups in a similar way. Orthogonal groups of characteristic 2. Over fields of characteristic 2 orthogonal groups often exhibit special behaviors, some of which are listed in this section. Any orthogonal group over any field is generated by reflections, except for a unique example where the vector space is four-dimensional over the field with two elements and the Witt index is 2. Note that a reflection in characteristic 2 has a slightly different definition. In characteristic 2, the reflection orthogonal to a vector U takes a vector V to V plus B, QU, where B is the bilinear form and Q is the quadratic form associated to the orthogonal geometry. Compare this to the householder reflection of odd characteristic or characteristic 0, which takes V to V minus 2B, QU. The center of the orthogonal group usually has order 1 and characteristic 2, rather than 2, since I equals minus I. In odd dimensions 2n plus 1 and characteristic 2, orthogonal groups over perfect fields are the same as symplectic groups in dimension 2n. In fact, the symmetric form is alternating in characteristic 2, and as the dimension is odd it must have a kernel of dimension 1, and the quotient by this kernel is a symplectic space of dimension 2n, acted upon by the orthogonal group. In even dimensions in characteristic 2, the orthogonal group is a subgroup of the symplectic group, because the symmetric bilinear form of the quadratic form is also an alternating form. The spin or norm. The spin or norm is a homomorphism from an orthogonal group over a field F to the quotient group F, F2, that takes reflection in a vector of norm n to the image of n in F, F2. For the usual orthogonal group over the rails it is trivial, but it is often non-trivial over other fields. Or for the orthogonal group of a quadratic form over the rails that is not positive definite. Galois cohomology and orthogonal groups. In the theory of Galois cohomology of algebraic groups, some further points of view are introduced. They have explanatory value, in particular in relation with the theory of quadratic forms, but were for the most part post hoc, as far as the discovery of the phenomena is concerned. The first point is that quadratic forms over a field can be identified as a Galois H1, or twisted forms of an orthogonal group. As an algebraic group, an orthogonal group is in general neither connected nor simply connected. The latter point brings in the spin phenomena, while the former is related to the discriminant. The spin name of the spin or norm can be explained by a connection to the spin group. This may now be explained of quickly by Galois cohomology. The spin covering of the orthogonal group provides a short exact sequence of algebraic groups. Here mu2 is the algebraic group of square roots of 1, over a field of characteristic not 2. It is roughly the same as a two-element group with trivial Galois action. The connecting homomorphism from H0, which is simply the group OV of f-valued points, to H1 is essentially the spin or norm, because H1 is isomorphic to the multiplicative group of the field modulo squares. There is also the connecting homomorphism from H1 of the orthogonal group to the H2 of the kernel of the spin covering. The cohomology is non-abelian, so that this is as far as we can go, at least with the conventional definitions.